Okay, you guys don't need to start by writing down this slide, but I want to kind of start and end kind of all the chemistry you guys have learned because we're kind of bookending this, right? This is the last topic that I've got for you in high school chemistry, and I want to, as I'm ending, I want to revisit one of the first things you guys learned about. This is what I talked about yesterday a bit. The idea of some of the chemical equations you guys first learned. In grade 10, I thought you guys grade 10, right? For science? I didn't teach you guys grade 10 though. But you guys should have learned in grade 10 the five main reaction types, and we've since learned so many more. But like you've got formation, decomposition, single, double replacement, combustion. But I want to add to this now because if you were in my grade 9 class or grade 10 class, we now know that life is a little more complicated than just looking at these equations and going, oh, well, okay, this plus this turns into this. Okay. For example, let me write down a few of the thoughts that we might have to consider. One of them would be excess and limiting reactants. For example, let's say we started with 400 grams of this, and we started with 1 gram of this. Will you make iron oxide? Yeah, but what are you going to be left with? A whole lot of iron. Does that make sense? And that was one of the things that when we first started talking about chemistry back, 2, 3 years ago, you never really would have considered that possibility. Excess and limiting reactants. It's something now that we can add to our list. Or, for example, if you're undergoing a decomposition reaction, sometimes things do compose, but we learned in our first unit in Chem 30 that sometimes it might require, say, an activation energy, right? Otherwise, just random stuff would start just falling apart in front of us, right? But if it wasn't for the fact that we now know that there's kind of a graph to this, whether it's endothermic or exothermic, everything requires that activation energy barrier that kind of gets things going, right? And so I guess what I'm trying to review here is some of the complexities to chemistry that if you were to talk to like your, sister or brother who's in grade 9 right now, they'd be like, hey, I learned this stuff. And you go, well, you kind of have, right? And I tell you guys this a lot when we learn chemistry is that I show you some stuff at first, but then later I can show you some more of the details that we really couldn't explain until you knew more. Here's another idea. In this single replacement reaction, we now understand the concept of a redox table and the idea of spontaneity. Although on paper I can write this reaction, what we really have to consider is copper strong enough to be able to work with this iron right here? Does that make sense? Maybe I should approach it the other way, actually. This iron right here, it is going to try to be reduced. And so therefore, it is an oxidizing agent. Is this iron oxidizing agent higher up on our table than the copper as a reducing agent? Because if it is, the reaction takes place. If not, it's not a spontaneous reaction unless I add some activation energy to get it going, which would be like the non-spontaneous cells. Right? And again, we wouldn't have thought about that in grade 9 or grade 10. For a double replacement reaction, one of the things that I tried to do in this example here, but I don't think I'm going to be very successful, but sometimes things can react in subsequent reactions. And so even though I can write this equation plus this one making this stuff right here, maybe I need to consider that what's going to happen is that this HCl is now going to react with something else. And then that something else is going to react with something else. And eventually we learned a concept called Hess's law, where we might suggest, well, if you have this on this side and this on that side, we can kind of add them together. Again, not something we learned about in grade 10. Another example would be in combustion. We learned in grade 9 or 10 about combustion, where it always makes carbon dioxide and water. But now we know that's not really true. Sometimes multiple reactions take place at the same time. For example, this could turn into CO2 and water. It also could turn into carbon monoxide and water. And it also could turn into just plain old carbon and water. Right? We also talked about the idea about how, let's say that I was working with this molecule right here, C2H6, is actually pretty basic. But let's say I gave you C4H10 as what we began with. What is C4H10? Well, it could be butane. It could be 1, 2, 3, 4 in a row. But it also could be a methylpropane. And we learned about isomers and how you could actually have the same chemical formula, but it could actually be something else. And these are actually different from each other. And with that, we learned the idea of, let's say you had C4H8, for example, and let's assume that C4H8 was, goodness, why is this not working? Try again here. Carbon, 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 carbon. This is one possibility if you threw a double bond there. because then you'd have 1, 2, 3, 4, 5, 6, 7, 8. But it also could be there. That's a different molecule entirely. Anyone know another way you can make a C4H8? There. And that's one of the things that when we're back in grade 10 again, when we wrote out this molecule right there or this one right here, we never really considered the fact that a C4H10 could actually look different ways. And not only that, but let's say I were to try to add to this Cl2. Well, now it really depends on what's going on here, because if I want to add chlorine gas to this one, what reaction takes place? But if you add Cl gas to this one right here, addition, right? And so I guess where I'm trying to go with this last unit here is I'm trying to wrap up our chemistry journey together. Boy, this sounds really like deep now. Hopefully I've taught you a lot more intricacies of chemistry that are beyond, what we learned about, 3 years ago. And now you understand that, yeah, multiple reactions happen, or reactions only take place if you add a catalyst. I didn't even mention that one yet, right? So the last thing I want to mention then is the whole point of this unit. So I'm going to go back to my slide now. I want to talk about the concept of equilibrium, where we like to assume when we write reactions, again, in grade 9 and grade 10, that A and B turn into C and D and they stop. But that's not always the case. Sometimes what occurs is these guys right here, they decide to get together and form the FeCNS molecule. And then they break back up. And then they get back together. This is that bad high school romance, TV show kind of thing, where they get together in season 1. They get together in season 1, but they break up in season 2. But then they get back together for a one-night stand in season 3, and then they break up. And then the finale, Ross and Rachel finally get back together. Friends, there's a good example. Sorry, we're watching Friends at home right now. So does that make sense, though, the idea here? And so this concept of equilibrium is something you wouldn't have considered. I have this slide right here that I think is a good analogy for how equilibrium works. Okay? Equilibrium does not mean that you have equal products and reactants. I'm going to say that so much over the next couple of days, because that's almost always one of the distractors on the theory question they ask. They're going to ask a theory question about what is equilibrium, and the answer is when the forward and reverse reaction rate is the same. It does not mean you have equal products and reactants. See how both of these ants right here are going to walk to a pile, this goes really slow, by the way. They're going to walk to the pile, they're going to grab a rock and put it in the other pile. From a macroscopic observer, do you see anything? No. Because if you were looking from a long ways away and you couldn't even see the ants, really no change is going to happen, right? You're just going to have one go from this pile to that pile there, right? But what happens if this ant right here were all of a sudden to pick up 2 rocks, whereas this one only brings 1? Well, what happened eventually? Yeah, this pile, I guess, would shrink and this pile would grow. Would we be at equilibrium at that point? No. So the question about equilibrium then is, well, how long did it take ant 1 and ant 2 to have their reaction rates kind of be the same? And I tried to draw this picture yesterday in my notes. Imagine that the forward reaction goes like with this speed, and then with this speed, and then with this speed. And then the reverse reaction takes place with the first guy kind of goes there, so not really all that fast. And then he speeds up and goes to there, and then finally he gets to being about that speed. Now we're at equilibrium. And the reason why is that the rate that we're talking about, this forward rate and this reverse rate, are now the exact same magnitude. But what should end up happening is we've made some products now. Does that make sense? The question is, did we make more products or more reactants? And so I want to start actually with some practice questions I have at the back of my notes here. Oh, where is it? Here we go. Where when I give you guys some numbers, we can do one of 2 things. We can either find an equilibrium constant. You guys don't have these, I don't imagine. I think these are just extra ones. So just write this down on the back page somewhere. Where what we can do is we can try to calculate, well, did we actually make more products or keep more reactants? Okay. For example, imagine that the reaction takes place for about 4 seconds before the reverse rate starts catching up. I imagine you probably didn't make that many products. Whereas, let's say the reaction took place for about 10 minutes, and then the reverse rate kind of kicks in. Well, now I imagine you mostly have products. Okay, and so what we can do is we can do one of two things. We can either calculate the equilibrium constant or the percent yield. Let's talk about them before we calculate them. If the equilibrium constant is 0, no, that's not what I want. If the equilibrium constant is between 0 and 1, what does it mean? What do you have more of? Reactants, yeah. And if the equilibrium constant is above 1, you have more products. And I didn't mention this one yesterday, but if it's exactly 1, you should have a 50-50 split then. Whereas if you have a percent yield that is below 50%, you have more reactants. If it's above 50%, you have more products. Two more possibilities, by the way. What if your percent yield is 100%? Which means there is no equilibrium. Now, there's two reasons why. One, it could be that equilibrium just doesn't happen in this example, or it's not a closed system. You do require a closed system. Final possibility, what if it's 0%? It's non-spontaneous, which is something we talked about in previous units. Oh wait, why don't we get started on this question because you guys are starting to beat me to this. We are going to take some ammonia. So ammonia is NH3. We're going to throw it in a sealed container. Sealed's important because it's got to be closed. And it already contains some nitrogen gas. What it looks like, though, is that ammonia is going to decompose. So we've learned this reaction back in grade 10. Ammonia decomposes into N2 and H2. And the equation would be, let's see, you need to put a 2 here and a 3 here. However, what ends up happening here is not all of the ammonia actually happens to turn into products. What ends up happening along the way is, yeah, the ammonia tries to decompose, but then it returns back into the beginning. So the common way I'm going to show you how to solve this is using what's called an ICE table. It's kind of like a crazy Sudoku, where you have to have like almost like columns. This particular one is like 9. It's like an X's and O's grid. It doesn't have to fit that pattern, but it looks something like this. Oh wait, one more thought I have to have for you. All of these are supposed to be concentrations. So when I give you 6 moles of ammonia, that's actually not good enough for us. We need to do a concentration, but I gave you liters, right? So we need to do 6 divided by 1.5. Oh, I never have a calculator nearby. Is it 4.5? All right, it was 4. So 6 divided by 1.5 means our ammonia began at 4 moles per liter. Okay. However, I'm going to throw a twist on this one here. Apparently, there was actually some nitrogen gas already there. Why would there maybe be nitrogen gas already in the container? What's air mostly made of? Hey, that makes sense. So you have 1 mole of nitrogen gas also in 1.5 liters. So 1 divided by 1.5 gives us 0.6 repeating moles per liter. And since it didn't say anything about hydrogen, I guess we're going to start with 0. Now this is a bit of a twist. I didn't give you one that looked quite like this yesterday in my notes, because I can't predict exactly what they're going to do in terms of questions. But does that make sense so far? So you actually have some product to begin with. Now it does give us one more thing, though. It says after we're done, there's 2 moles of nitrogen when we're finished. So 2 moles in the 1.5 liter container is 1.3 repeating, which means that eventually you have 1.3 repeating moles per liter. I think you're going to pick up on how this works pretty easily. Once you have any top row number and its corresponding bottom row number, you have enough to fill out the table. Because then the whole idea is, well, how much did things change? So how do you get from 0.66 up to 1.33? Well, that works. What did you go up by, though? You're right, you did times by 2, but how much did you add? I think it's 0.66, isn't it? Yeah. So you added 0.66 moles per liter. Okay. Well, now that you know the middle column, change is dependent on the coefficients. For every 2 of these, you make 1 of these and 3 of these. So I can now figure out the rest of these columns here based on the ratios. What is 3 times bigger? I think 3 times bigger for this is actually 2 moles per liter. Because like from 1 to 3, 0.66, yeah, times 3 is 2. And 0.66 doubled is 1.33. Now, watch the signs though carefully. We should be making more products, but what happens to our reactants? We lose our reactants. So now to fill out the table, when we're done, just based on the way the ratio works, you're actually going to have more hydrogen than you actually have nitrogen. And then this guy right here is going to be what, 2.66 moles per liter? You guys follow that? Okay. So to finish off question A, part A asked, how many moles of hydrogen gas are there at equilibrium? Well, there's 2 moles per liter times by 1.5 liters. Yeah, so for part A, there's 2.0 moles per liter. But don't forget, your container is 1.5 liters. So 3 moles. We should actually probably do sig digs. I've been kind of cheating on sig digs the whole time. It looks like every single number I originally was given was 3 sig digs. So I should probably make it 3 sig digs. That one's not too bad. Okay, part B. What was favored? The reactants or the products? Well, there's actually 2 ways we should be able to try to figure this out. The equilibrium constant is really the one you're supposed to do. So we'll do that one first. The equilibrium constant basically says to write this equation here. You want your products written over top of your reactants. And so your products, one of them is nitrogen gas, and the other one is hydrogen. Only hydrogen has to go to the power of 3 because you make 3 every time you make something, right? And then your reactants is your NH3, and you need to square that. So it's actually pretty easy to do now. Take your concentrations we just solved for. Make sure you use the equilibrium concentrations, though. Because if, remember, go back to my ant. I won't flip the slides. Remember the ant that was carrying rocks back and forth? Once you reach equilibrium, those concentrations are not changing anymore. They are now stuck. Is stuff still happening? Yeah, the forward ant and the reverse ant are still moving stuff. But so, anyways, nitrogen was what? 1.33 repeating. Hydrogen was 2 to the power of 3. And our initial amount was 2.66 squared. 1.33 times 2 cubed divided by 2.66 squared. I got, I better do it more exact actually. 1.3 times 2 cubed divided by 2.6. Okay, I got 1.50 with my sig digs. Okay, a couple of reminders on this. This right here has no units. It's considered a constant. And all we can do is use it for comparison purposes. What's favored, products or reactants? Yeah, apparently you made more. Oh, what did you say, Darian? Oh, you're wrong then. It's products. Sorry. Oh, that's what I meant. Yeah. Yeah, you make more products. Is that clear to everybody else? Okay. The harder one's probably the percent yield. If I want to do the percent yield, I got to do what it actually was divided by what it could have been times 100. Pardon me. Why don't we use nitrogen as our one to test for? Or sorry, my hydrogen for how much I tested for. How much hydrogen did I actually make? 2 moles per liter. So I actually made 2 moles per liter. How much nitrogen could I have made, though, how much hydrogen could I have made if all my ammonia had reacted? How much hydrogen could I have made if all my ammonia had reacted? You're right, 6, yeah, because here's the rationale. You started with 4, and there is a 3 to 2 ratio going on. So you could have made 1.5 times as much, which is 6. Should I say that again in case you didn't catch that? You started with 4, and then you really just have to focus on the coefficients. 2 would have turned into 3. So like a 3 to 2 ratio on your 4 means you could have made a max of 6 moles per liter. So 2 out of 6 gives us a percent yield of 33%, which does sometimes perplex people because they're like, hang on, that's less than 50. One of the reasons why, though, is you have to consider the fact that you also made some nitrogen as well. So it does become a little bit more complex. And the other thing I need to point out is that there was also nitrogen to begin with. And that also throws things off, because since there was already nitrogen here to start with, you weren't capable of making as much as you wanted to. Because, like, if you remember the ants in the pile sort of thing there already were rocks in the far pile. So this equilibrium was going to start slowing down before you even wanted to. So although I do like percent yields, truthfully, when you want to figure out whether something is favored, the equilibrium constant is technically the right way of doing that. Okay? Well, that's the issue, though, is that since nitrogen already began with something, like a percent yield kind of isn't really fair. You know what I'm saying there? Because, like, you already began having some product there. Well, and I think that's the reason why this one right here was lower than you'd expect it to be. So, just so you guys are aware, I might ask you to calculate a percent yield once in a while, but really, we only ever really do equilibrium constants. So, okay, let's try another example here. Once you know equilibrium constants, what's useful about it, and this is something you're going to get on your diploma, I guarantee it, there's always one of these. If they give you an equilibrium constant, or, by the way, there are some in your data book. They're found in the data book under the acid table, and we'll get to that a future day. If you know a constant, you can actually work backwards and figure out how much product or reactant to expect. And this was the example I did right at the end of last day's class, and I was kind of rushing it. So let's try this one a little bit slower. I'm going to give you the equation we already need. So carbon dioxide is going to turn into carbon monoxide and oxygen. It says it's in a sealed flask, and it kind of says it's at equilibrium, so I'm going to throw the double-sided arrow on them. First thing I need to make sure I do, though, is this thing's not balanced. So if it's not balanced, make sure that you balance it by going, say, 2 and 2, and that's it, right? Yeah, 2 and 2, and 1. So start there. Then we need to make our ice table. But today's ice table is a bit different. It says that there's 4 moles per liter right here. And if it doesn't state that there were products already there waiting for us, like it was in the last example, we'll assume there's 0. But that's all it gave us. That's literally the only numbers that we were given, other than this equilibrium constant. But the constant is actually enough for us to be able to make a prediction as about what's going to happen. Because what's going to happen to your carbon monoxides and your oxygen, they should increase. Now, I don't know how much they're going to increase. I predict it's going to be a significant amount. And the reason I predict that is because this constant, 1.95, is above 1. So I don't expect that when I'm done, that these two things down here are going to be like 0.0003. I expect I'm going to have 2 or 3 moles per liter when I'm done. But really all I can do is suggest that, well, this is going to go up by an unknown amount and finish with that unknown amount. And this is also going to go up. Good. By 2x. And that means that this is going to go down by 2x. Sorry, there's algebra in your chemistry. It kind of got mixed in there. Yeah. Like I said yesterday, though, I am confident because I know I taught you guys the skills you need in math at some point. So I'm very sure. Okay. So in order to solve this, the next thing we need to do is write out our equilibrium equation, which is this. The Kc value is equal to oxygen gas's concentration, carbon monoxide's concentration squared, all over carbon dioxide's concentration squared. Okay. Oh, thank you. Right here. Thank you. Good catch. Totally didn't notice that yet. Would have caught that later, I'm sure. Okay. So, all I can really do then is put in most of my variables. Carbon monoxide is 2x, and that gets squared. Oxygen is just a good old-fashioned x. Carbon dioxide was 4 minus 2x, and that's squared. And then our Kc value, we actually knew, because it told us the Kc value is 1.95. Yay, this looks like fun. All right. This is actually the one I gave you here, just so you guys are aware, is beyond the scope of what they're going to test you on the diploma. And I'll show you why it's beyond what you're expected to do. If you wanted to solve this, you have fractions. You guys remember how to solve fractions? Cross multiply. So cross multiplying should be some of what you try to do. Over here, in the right-hand side over here, you're actually going to have 4x cubed. Because the 2 will square to make 4, and then there's x squared here plus 1 more there, so you're going to have 4x cubed. And when you bring this thing over to the side over here, I'm going to FOIL it out. So I'm just going to do a little bit of work here. It's going to be 4 minus 2x next to another 4 minus 2x. So it's going to be 16 minus 8x minus another 8x plus 4x squared. We got cheese, muffins, yogurt, apples, bananas. They're in. All right. We got a few. We got a customer. Thanks, guys. All right, we're going to get to this point right here. Can you guys handle that math there? I cross multiplied and I FOILed. I know you guys know how to do at least those two steps because I'm sure I've taught you all that. So I FOILed the 4 minus 2x squared, which gave me, I changed the order. I gave it 4x squared minus 16x and 16. Don't forget, you still have to times that by 1.95. I'm actually not going to do that right now, though. I'm not really thrilled about that. I'll do that later. And then the right-hand side is just the 4x cubed. Here's why this is beyond the scope of the diploma. They will only make you go as high as a quadratic. You guys have your data booklets nearby? Turn past the periodic table one more page in. At the bottom, where is it? Okay, on page 3. Is that 3 right there? Yeah. On page 3, see how right dead center in the middle of the table there is the good old quadratic formula? They give that to you possibly for a reason. Because when you're solving this specific section right here, as long as they make it a type of question that is quadratic, you can then solve it using the quadratic formula. Okay. However, this one's beyond the scope of what they would assess you on. I just made this one up myself because this one's actually cubic. So you guys in grade 12, we know how to solve cubics. But here's what I'm going to suggest we do just for this question. And by the way, though, you could do this on the diploma when you need to solve something like this. Use your graphing calculator and find where they intersect. So like, for example, type in 4, well, actually, maybe do this, actually. I got a better idea. We'll solve for x-intercept still. Expand the 1.95 across all these terms here, maybe. So 4 times 1.95 is 7.8x squared. I'm going to put that on the other side and make it negative 7.8x squared. 1.95 times 16 is going to give me, okay, when I bring it the other way, it'll be positive 31.2x. And I guess when I bring that one the other way, it'll be minus 31.2. You guys follow what I did there? I expanded this by timesing these by each other. And then once I did that, I brought everything like to the other side. I now have a cubic equation. If it was quadratic, you could solve it using the quadratic formula. So do you guys get how this is going to be beyond the scope of what they would require you to do? So all we got to do now is to solve this. So like just type this in then. 4x cubed. What's next? Plus 7.8x minus 7.8x squared plus 31.2x minus 31.2. And what I'm trying to do is solve for where that equals 0. So really what I'm actually being asked to do is find x-intercepts. But you know how you find x-intercepts is you go second calculate zeros. A couple things I want to change though before I get there. X is what we're solving for. I can actually tell you the maximum value of x that's allowed. The maximum x value that's allowed is 2. Can someone explain to me why x cannot be more than 2? Yep, good. I think what Max is pointing out is this right here. All you have is 4, right? That's how much you have to begin with. And if x is 2, 2 times 2 and 4, you'd now have lost everything. So the only reason I'm suggesting this is when I do my window size, let's go from 0 to 2, and that's really all I need to consider. So if I go second, calculate the zeros, hopefully somewhere in here is going to be an x-intercept. Boom, found an x-intercept. If you guys remember how to do this, go on the left-hand side of the line, go on the right-hand side of the line, and it's at, call it 1.13. You guys able to replicate that? So, if I go back to my table, I now know what x is. This was 1.13, which means this would be double that, so 2.26. And then 4 minus 2 times 1.13 would give me 1.74 left. So this is harder than you need to be able to solve because it involved a cubic. But the basic premise still applies. So once I give you guys a second to kind of catch up here, I'll re-go over my steps there. If you are given a KC value, or if you can look it up in a data booklet, what we can do is we can write ourselves an expression like this, where we're going to throw x's into here. And it's always going to work the same sort of way. You're always going to have a constant number sitting here, and you're always going to get an expression here that involves x variables. Chances are it's going to be squared. Not cubed, though, because they don't require you to go to cubes. What you're going to do is you're going to cross multiply. You're going to FOIL the crap out of everything and get yourself one big equation. If this thing didn't have that there, you could solve this using the quadratic formula. Although, to be honest, I think it's probably just faster still to graph it to see where it solves. Okay. By the way, I should point out, when you guys use the quadratic formula, know how you get more than one answer? You can only accept answers that are within, remember how like Max pointed out that my max value of x could have been 2? When you get more than one answer, one of them is extraneous because only one of them will fit within the range we're actually considering. So, that makes sense? Yeah, let's leave it there. Let's go to my notes for the day now. I'll give you guys more practice on that over time. Today's lesson, by the way, is all it's all theory. Yeah, there's no math to this. It's all basically written notes. And so I'm going to spend most of my remaining time here using my analogy, this is the best one I've ever come up with. It's not perfect. I know there's some issues here. But in order for me to teach you this concept, imagine that there's a bus stop and a bus. Okay? And so what's going to happen is as the bus drives around the city, kids are going to get off the bus, kids are going to get on the bus. Now, if we're talking about an equilibrium system, if 5 students get off of a bus at a bus stop, how many better get back on? 5. Because if 4 get off and 3 go on, and 7 get on and 2 go off, eventually the bus will become either full or empty. Okay? So to begin with, I've got a couple of just random people that I've got here just to illustrate the concept. Imagine that as the bus goes around the city, you would not notice anything from a macroscopic point of view, because say there's a few people at the bus stop and there's a few people on the bus, and I'm going to specifically make it not the same number, because if I made it 3 and 3, you might think that's why it's equilibrium, so I'm going to make it 3 and 5. Okay? If at the bus stop you get off, you better get on. And at the next bus stop, if this guy gets off, that one better get on. Okay? That's what makes it equilibrium. Does that make sense? Okay. What I want to talk about today is a concept called the Chatelier's principle, which is all about stress. And stress basically means something that you do to the system to change things. I'm going to talk about 3 things we can do, and I'll use my analogy to start here. Let's talk about what would happen if all of a sudden it became really, really cold outside. Well, you know how we normally had a ratio of 1 person getting off for 1 getting on? Maybe a few people that are outside are kind of like, oh, it's cold. So rather than 1 on, 1 off, what might end up happening for a temporary while is that 2 might go on and 1 off. And then 2 might go on and then 1 off. And I didn't actually put enough over here to kind of account for this. And so what's going to happen is a little bit of a shift's going to occur where eventually you're going to have more people getting on the bus because, well, it's warm on the bus, it's heated. Okay? Now, eventually the equilibrium will catch up, and then when 2 go on the bus, eventually 2 will come back off again. And when 2 go on the bus, 2 will come back. Ooh, the bus moving. 2 will come back off again. Okay? But the idea is that for a temporary period of time, a few extra people are going to shift. That's the word I'm going to use a lot. They're going to shift this way here due to the fact that the cold causes them to want to go one direction or the other. Now let's use the opposite example. Let's say that all of a sudden it's nice out. Well, normally the ratio was, okay, 2 get off the bus, 2 go on. 2 come off the bus, 2 go on. But all of a sudden it's nice outside. So maybe what ends up happening is for a temporary little while, 3 come off the bus and 2 go back on. And 3 come off the bus. Oh, stay there, bus. 3 come off the bus and 2 go back on. Now what I've done is I've started shifting this direction here. Eventually the equilibrium will catch up, and so what will happen is when 3 leave, eventually 3 will come back again. But the natural tendency would be, well, if it's nice out, wouldn't you want to go outside? Does that kind of make sense as a metaphor? The same sort of thing then happens in reactions, because all reactions are either exothermic or endothermic, hence the heat or the cold. And what ends up happening is when we either heat up reactions or when we cool them down, a temporary shift occurs. And basically it starts to create more products or less products as you go along. And I'm going to show you that more on future slides, but I'll just leave that there for now. That's one type of shift that can happen. It's a heat shift. Let me use another example, an analogy. Imagine again that you've got all these people that are either on the bus or off the bus. And let's just make sure that I've got an unbalanced ratio so it's not like even there. All of a sudden, the bus that you were working with, let's say that all of a sudden it's bigger now. There's more room on the bus. Which way do you guys imagine this is going to shift? Towards. Because what's going to happen is normally it was like 1 on, 1 off, 1 on, 1 off. But all of a sudden people start catching wind. Hey, this is a pretty nice bus. There's like TVs in there. There's there's a free Wi-Fi. Well, all of a sudden what ends up happening is, well, now maybe 2 go on the bus as 1 come off. And 2 go on the bus as 1 come off. If you like my ant analogy, You know how the ants were each carrying one rock each way? Well, all of a sudden, one of the ants decides to carry two rocks for a while. But eventually, it catches up. And so, although it was a 2-for-1 ratio temporarily, at equilibrium, eventually it becomes 2-for-2. And we're back to a normal spot where it's 2 and 2 and 2 and 2. And do you notice a difference anymore? No. But you know what's happened all of a sudden now? Hey, there's more kids on the bus. Why? Well, because there was more room there. Here's this analogy then. If you all of a sudden increase the volume of a flask, which normally has been constant. You know how in my example there, I gave you a 1.5 liter flask? Well, what happens if all of a sudden I could expand its volume somehow? Or what if I could increase its pressure or decrease its pressure? Those things are involved. Because here's the opposite example. What happens if this bus all of a sudden has to get downsized to like something much smaller? Well, all of these people they're all squished on there now, right? And so what's going to end up happening is it was a 1-for-1 relationship. 1-for-1, 1-for-1, or 2-for-2, or 3-for-3. I don't care what the rate is, right? But all of a sudden now it's going to be like, well, now let's go 3-for-1 and 3-for-1. Now, if we keep going at this rate, what's going to happen to the bus, though? It'll be empty. It won't ever empty out, right? So eventually, at some point, equilibrium will kick back in and say, you know what, I know we were trying to do 3-for-1, but now it's actually going to be 3-for-2. And then eventually it's going to be 3-for-3. So 1, 2, 3, 4, 1, 2, 3. Right? But now the shift that's occurred has now gone this way. So that's the second thing. You can have heat temperature shifts. You can have pressure volume shifts. And then the third one you can have involves basically adding like an excess of reactant or product all of a sudden. So I'll just split these guys up. Here's the third one. Imagine that here's the scenario. And again, there was like a 1, 2 to 2 changing. So 2 go on, 2 go off. 2 go on, 2, right? And let's say that all of a sudden, a whole bunch of product got dumped in. So there's all of a sudden a whole bunch more now sitting here. Well, all of a sudden, this bus stop is overcrowded. Right? Who wants to be at this bus stop? It's overcrowded. Now, the bus might look crowded, but in the grand scheme of things, I think I'd rather take my chances on the bus than crammed here, right? So what would happen is, again, a temporary shift where, okay, so a few will go this way, and a couple will come back. But then a few will go this way. 1, 2, 3, 4, and a couple. Oh, goodness gracious. Let's lock this in place. And then a couple will come back. And maybe 4 will go this way now. And then maybe 3 will come back. And now 4 will go this way. And now 4 will come back. And as soon as I get 4, 1, 2, 3, 4, and 4, now we're back to equilibrium again. But what happened? Well, let's shift towards the bus. Okay. Or what happens if all of a sudden, all of these people, they just decide to leave? And all of a sudden, these guys, they're all gone. Well, now there's a deficit over here. There's a lack. And so what's going to happen is the shift is going to go this way, where a few are going to go this way, and a couple will come back. And a few will go this way, and a couple will come back. And a few will go this way, and a couple will come back. But if you guys notice what I was doing 4 for 3 there. Does that make sense? And eventually, though, it'll become 4 for 4, and now we'll be back at equilibrium. Okay, but what happened was a shift this way. Okay, I want to talk to you guys a little bit about history problem, then I'm going to go through my notes. What time are we at? Okay, I got lots of time. This is pertinent back to World War I. Okay, back in World War I, you guys studied a little bit of wars, right? You guys do World War I and 2, or is World War II just in social 30? Grade 11s, what do you guys know about World War II? You guys know a little bit about it? Do you know like how the Nazis were able to win in World War II? Well, sorry. How they were able to start winning in World War II. What was their strategy? Sorry, good call. How did they get their huge advantage? What was their technological advance in World War II? Tanks. You guys talk about Blitzkrieg? Okay, well, okay. Okay. In World War II, The reason why Hitler was so successful is that the Germans perfected a technique called blitzkrieg, where they just used their tanks and they just like ran right through everybody. And the reason why it caught everybody by surprise is because in World War One, the warfare was quite different. They engaged in World War One in something called trench warfare, where literally you dug a big ditch on your side, they dug a big ditch on their side, and you shot artillery shells over trying to hit each other, and you bunkered down. And every once in a while, you decide to get up, brave the battlefield, and run across the line and try to go kill them. But the problem is that like you'd get shot down as you tried to like cross the middle area. Does this make sense? You guys know a little bit about this or seen a war movie? World War II is different because Hitler said, screw that concept. We're just going to send our tanks right through you guys and blitz through you. Okay. I want to talk about World War I for a bit, though. The reason why this was relevant in World War I is because they went through a huge amount of munitions or explosives. Because literally, that's what they did. They kept shooting artillery shells and rocket shells from one side to the next. But in order to blow up bombs, you need to have explosive materials. And at a certain point in World War I, the world was starting to run out of explosive materials because they just kept using all of it. Does that make sense? So it was, I believe, in the year 1917 or 1915, somewhere around there, sometime in the middle of World War I, a guy named Fritz Haber came up with this process where he could make ammonia. And ammonia is very explosive. Okay. The problem with his making ammonia is that, well, actually, let me start with the easy part. The easy part about making ammonia, which is explosive, explosive, is that it requires nitrogen gas, which is easy to find because it's in your atmosphere, and it requires hydrogen gas, which is actually not that hard to produce. Here was the problem then. This is the reason why Germany didn't actually end up winning the war in the long run, is that although you can try to make ammonia, equilibrium kicks in and it turns back to your reactants. And so when he tried to produce more ammonia for them to work with, he might have started with, say, like 100 kilograms of this stuff right here, and it tries to make, say 100 kilograms of this stuff here, because conservation of mass should hold, but it turned back again, and he only ended up making, say, like 22 kilograms. And then what would be left? 78 kilograms starts here. Well, that was very frustrating. But they discovered Le Chatelier's principle. And the basic idea is, well, we can mess around with things due to stresses. For example, let's say that you want to manufacture, in this example, this is ammonia, this is explosive. Let's say you want to manufacture more ammonia. One of the things you could do is change the temperature. And if I manipulate the temperature, I could force a few more kids onto the bus. Does that make sense? Or I could mess around with the volume. And if all of a sudden I change, I can't change the volume anymore because I locked this thing in place. But if I mess around with the volume, I can produce more. And so this helped them to make more ammonia. But it wasn't able to make like everything, not all of this stuff truly turned into ammonia because it started changing back again. Okay. So eventually this became known as the Haber process. And it helped make more munitions, specifically during World War I, when they were really required in order to continue fighting. Because really, at that point, again, I don't know how much you guys know about World War I, but World War I was really a war of whoever was going to run out first was going to lose. That's really what it was. It was a stalemate. No one was really advancing on either side or the other. And so the side that was going to run out of food or medicine or soldiers, really, that was the side that was going to lose. World War II was fought quite differently. So, does that make sense? Let me go through my notes now, because I've finally actually covered the analogies I want. Le Chatelier's principle, then, is what can cause a shift. Do I have the word shift on here? How about this? The system reacts in a direction that opposes the change. Okay. For example, when I made the bus bigger, the reaction shifted towards the bus. When I made the bus smaller, the reaction shifted away from the bus. Okay? And so what ends up happening is it always shifts, and there's these three things you need to know about. There's the concentration shifts, the temperature shifts, and the pressure volume shifts. Now, let me just go through my notes, I think, at this point here. So let's start with concentration. Let's say that you add a whole bunch of excess reactant to the system. So I'm going to write it as a basic equation. A turns into B. But B turns back into A. But then A turns back into B, and B turns back into A. What happens if you add a whole bunch of extra A? Which way would the system shift? Towards A or towards B? towards B. Because in my bus analogy, a whole bunch of new kids just showed up at the bus stop. So what ends up happening is, well, all of a sudden the forward rate becomes just a little bit bigger. And so some A is turning into B, and I know B is turning back into A, but because you have so much of this stuff, you have more than you're expected to, the forward rate kind of goes a little bit faster. And slowly but surely, the reverse reaction rate eventually catches up until they're even again. But what that does is it makes you more product, which in the Haber process was useful because they needed it to blow things up. What happens if I somehow could find a way to remove some A from the process? Which way would it shift? Towards A. Because what really, there's a lack over here. And so what ends up happening is this reaction rate says, okay, I'll make this reaction rate just a little bit bigger to compensate. Now I'm going to try to make up for the deficit you have here. And so 5 changes into 4, and 5 changes into 4, and 5 changes into 4 until eventually 5 changes into 5 and it recatches up again. But in the meantime, you've now remade some A. So in a way, this is how this might look in a graphical form. You were at equilibrium. This stuff was trying to change into this stuff, and you tried to change it, and it hit an equilibrium. And then right here, we did something. We dumped a whole bunch of HF into the system. So all of a sudden, there's a whole ton of hydrogen fluoride in the system. Well, what's going to happen is there's so much extra HF in the system that it's going to actually increase. It's going to increase the forward reaction rate a little bit. And so what ends up happening is these guys right here, we start making even more of them. At this point here, we had maxed out. This was as much as we were able to make of our 2 products. Because these guys are my products, this guy's my reactant. So my 2 products were maxed out. But by dumping a whole bunch of HF in, HF's going to decrease a little bit. So this side's going to become a little bit less. And the other 2 sides get bigger. Quick question. Why is CCl4 not included? I haven't covered this yet. It's actually in my notes, if you've read them over by chance. But, yeah. In order for us to actually change your concentration, you have to either be a gas or aqueous. Liquid things and solid things, you can't change their concentrations. Aqueous things, you can change their concentrations because aqueous things involve ions being dissolved in water, probably, right? And so if you're dissolving ions in water, you can just dissolve more ions in water or less ions in water. So you can totally change the concentration of aqueous things. You can also change the concentration of gases because gases are compressible, right? Because concentration is how many moles you have per liter. I can change the volume of gases. But liquids and solids, you can't actually change concentrations of liquids and solids. So just as a note, anything liquid or solid never gets considered in one of these. By the way, it also does not get considered in ice tables. Whenever you're doing the math, if you have something that's liquid or solid, it is not considered important. Here's kind of another way of visualizing what happened then. The forward reaction rate and the reverse reaction rate eventually sped up. It used to be like, say, you made 5 for 1, and then 4 for 2, and then eventually it was 3 for 3. Right? And now you had a nice even exchange. As ants were taking the rocks one way or the other, or as kids are getting on or off the bus, it was even. But then all of a sudden you dumped a whole bunch of new reactant in, right? Well, now rather than having a 3 to 3 reaction rate, we have a 4 to 3 reaction rate. And what that does is it makes more products until eventually it catches up and it goes 4-4 again. But in the meantime, you've now made a little bit more product than you had before. Temperature is another one. All reactions are either endothermic or exothermic, right? And in a way, we've learned about this in our first unit, where if I have A plus B equals, say, C, I can either put energy, like, say, 37 kilojoules, I can throw it on this side over here and make it exothermic, or I can throw some energy on this side over here and make it endothermic. So, as an example, let's say I've got this reaction right here, and this reaction happens to be exothermic. What happened? Well, this ratio finally balanced out. Everything was nice and even. And then all of a sudden, the SO3 spiked, and these two dropped down. Did we increase or decrease the temperature? Did we increase or decrease the temperature? decreased it. Is that what you said? We decreased it. Let me show you why. Let's say you drop the temperature. There is now a deficit on this side here. There's a lack over here. And so what it's going to do is it's going to shift this way. This arrow is going to become slightly bigger because it produces energy. And so if you drop the temperature, it's going to try to heat itself back up by making more energy. And so the shift goes towards the side there's a deficit of. And so what ended up happening was it tried making more SO3, and therefore you had a little bit less of the SO2 and the O2. But eventually it caught back up again, and the forward and reverse reactions became equal. But in the meantime, you actually managed to make yourself a little bit more. Let's try the opposite here. I know this isn't what the graph shows, but hypothetically, let's say you increase the temperature. Well, if you increase the temperature, you now have more energy at your disposal. And if you have more energy at your disposal, there's too much stuff on this side, it's going to cause a shift this way to kind of use it up. And it's going to try to make more of these guys here. In general, here's how I like to show this. I'm either going to put an up arrow or a down arrow. If I put an up arrow, you shift away from it. If I put a down arrow, you shift towards it. Because if you have excess something, you try to use it. If you have a lack of something, you try to make up for it. I have a little note here. Your Kc value, by the way, is temperature dependent. Whenever we try to find one of those Kc values, it does depend on temperature. I don't know that this will ever come up, but if you ever change the temperature value, you change the Kc value. Let's talk about gas volume changes then. This is where you either make the bus bigger or make the bus smaller. So you change how much room there is. If you make the bus bigger, which way is it going to shift? Towards the bus, because there's more room there, right? If you make the bus smaller, it's then going to shift away, right? And so here's what you need to do. You need to count out how many gas molecules you have on both sides. Only gas molecules, because gases are the only things that can compress. Aqueous things cannot compress. Solids and liquids, we already kind of mentioned, cannot compress. So all we got to do is count the gas molecules on both sides and figure out which side actually has more or fewer gas molecules. So I got an example here. Let's say we've got SO2 turning into SO3. Which side has more molecules? Which side has more molecules? This side. Because in the net total, there's actually 3 molecules on this side to 2 molecules on this side. So if we're going to cause these two things to go down, it means we must have shifted this way, right? Because look at this graph. See how the SO3, we're getting more SO3, and we're getting less SO2 and less O2? It means we must have found a way to somehow speed this reaction rate up. What did we do? Did we increase the volume or decrease the volume? Decrease the volume. The reason why we decreased the volume is that if there's less room, would you rather be on the 3 side or the 2 side? We'd rather be on the 2 side, so it shifted that way. If there was more room and you increase the volume, then it would shift to the side where there's more molecules. So what happened on this one here is there must have been a decrease in volume. And I can actually show you that another way, by the way. See how all of these concentrations spiked? You know how concentration is moles per liter? But if you decreased the liters amount, well, all of a sudden the concentrations would all of a sudden spike because you'd have less space, right? Everything used to be in this amount of space. Now it's in this amount of space, so it's highly concentrated. So all the concentrations spiked, and then if you had the choice to be on the 3 molecule side or the 2 molecule side, and there's not a lot of room, you'd shift to the 2 molecule side. This is going to take a little while to kind of work through, by the way. Like, please don't feel bad if you don't have it yet. I'll give you lots of practice questions on this. Here's another visual of this one here. This is the example I actually showed you in yesterday's notes. The N2O4 and the 2NO2 gas. let's say that you increased the pressure, because that's really what's happening in this diagram here. Here, you're pressing the syringe in and you're increasing pressure. If you increase your pressure, it means you've now decreased your volume. So now there's way less space. Which way should this reaction shift if there's now less volume? You basically got a 1 and 2 shot at it. Is it going to shift left or right? You're right, it's left. And the reason why it would shift left is because there's less space. And if there's less space, it's going to shift to the side where there's less molecules. I want to go back to the Haber process real quick. This is actually what Haber figured out. It was N2 plus H2 turned into NH3. And the way you balance it is to do this. What did Haber do to his pressure or volume? Let's talk about volume. If he wanted to make this reaction take place, what should he have done to the volume? Yeah, he made the volume smaller. Effectively, what he did is he increased his pressure. And Haber realized that if he increased his pressure, he was actually able to make more products. Find me your data booklet. Go to your first unit table. You guys remember the table that has all of the endothermic, exothermic values on there? Find ammonia. You know that table there that has the kilojoules for mole value? What is ammonia's value? Now, that's a formation table, right? Okay. So the formation value was, what was it, negative number? Okay. That means it's exothermic, right? Which means that I should put heat on this side here. What should he have done? What did Haber do to the temperature? Increase or decrease the temperature to make more yield? Decrease is right, because if you drop the temperature, then it shifts this way, trying to make up for more of it. So Haber figured out the best way to make more of his explosives was to up the pressure, decrease the temperature. And while he was at it, he just kept adding in more reactants. Because if you add in more reactants, it also shifts this way. I don't remember what the number was, but I think he was able to get the yield from like the low 20s up into like the 50s or 60s, which was significantly more, and it helped prolong the war effort. Yeah, I think I read somewhere, but don't quote me on this, that Haber was actually, it's believed that he might have actually helped prolong the war by like an extra year or so, by like this process working. But don't quote me on that. I'm trying to remember what I read. Okay, what else do I got here? Catalysts. That's the last thing here. We've been talking about catalysts as we go along. Catalysts literally do nothing. And here's the reason why. A catalyst speeds up the reaction rate, but it speeds up both reaction rates. Remember the ants that I had going both directions? You know what a catalyst would do to the ants? It would make them both go equally faster. So the forward ant would run twice as fast, but the backwards ant would also run twice as fast. So this is always a question on diplomas. They ask you about catalysts. Catalysts do nothing. Okay? Catalysts do not affect your start and end position of a graph. Like a catalyst makes it so that rather than having to have this much activation energy, you can have less. Okay, but a catalyst does not make the reaction happen. Like it doesn't. In equilibrium, it makes the forward one happen faster, but it also has the reverse one happen faster. So catalysts do nothing basically. So I think this is my final chart here that kind of has just a summary of everything. Can I, with the 5 minutes I have left here, I got about 5 minutes, right? I do like a couple of made-up examples to kind of practice this. Yeah. So let's do just this generic example here. I'm going to go A plus B is going to turn into 2C plus D, and let's make all of them gases. And I'm going to make this thing be an endothermic reaction, so I'm going to put heat on this side here. Okay. Here's what I'm going to ask you. Tell me the shift under the following circumstances. Let's say that you add A. Let's say that you remove B. Let's say that you heat it up. Let's say that you decrease the pressure. Let's use those four. Tell me which way it would shift under the following four conditions. And I'll give you guys a second to kind of think them through. There's really no work to this. It's just kind of, you look at it and you go, well, it's this one here. So. The shift when you add A, remove B, heat it up, or decrease the pressure. I don't, by the way, mean to do all four of them at once. I mean, let's do them one at a time. By the way, when we come back from May long weekend, we're going to do a lab on this, where this is literally what I'm going to do. I'm going to make an equilibrium, and I'm going to use one where color change is observable. And so one side of the equilibrium is red, one side is yellow. And we're going to be able to see the way it shifts. I'll even do that here. Let's say that these things right here are red and these are yellow. Okay? And currently it's orange. Okay? As you add A, what color is this going to be? Red or yellow? That's going to turn red. Because here's what's going to happen. If you add a bunch of A, what's going to end up occurring is there's so much excess on this side that it shifts this way, trying to compensate, and it's going to make more red products. If you remove B, and you create a deficit here, what ends up happening is there's a gap, there's a lack over here. Sometimes I use a silly analogy. B got robbed. And so you know what happens? These guys over here are very generous, and they say, hey, why don't we speed up our reverse reaction rate just a little bit more and try to make a little bit extra for you, just to kind of compensate. It's not going to make you back to where you were when you started, but at least it helps get you caught up. And eventually it evens out. So this one would turn yellow. What would happen if you heated it up? Well, if you add more heat, it would shift that way. So then you'd get more red color. That's not red, but that looks good. Last one's probably the hardest one. You got to count up molecules on both sides. There are 3 total gas molecules on this side to 2 on this side here. Because there's 1, 2, 3, and just 1, 2 there. If you decrease the pressure, what did you do to the volume? Okay, so you've now increased your volume, which means there is more room. If there's more room, which side would you go to? Because if there's more room, then go to the side with 3. So this would be red. And that's probably a good a spot as any for me to leave it here. So when you guys come back, I'm going to do a demonstration where it's not really a lab where you do anything. It's more of a me do things lab. I'm going to get a whole bunch of control solutions, and I'm going to do tests where I'm going to like heat them up and cool them down. I'm going to increase and decrease their volume. I'm going to add and remove reactants and products, and we're going to see by color change which way things shift. Does that make sense? Okay, cool. There's really not much for you guys to do over your long weekend in the class unless you still have things you want to finish from the last unit. So just to remind you guys, for this current unit, I'm going to give you guys 3 quizzes. I'll let you do lots of practice on this one. 3 quizzes, just 1 assignment and 1 lab. That's it. Okay, so I guess finish up any old labs. And I mean, whenever you get finished your research paper, you get finished. Okay, like I don't need it tomorrow by any means, but maybe don't leave it until June 30th or anything. So. If we don't lose class, I did have that 1 day set aside for there to be a lab, but I'm not going to do that second lab. I could maybe set that day aside and rebook the laptops for kids if you want to finish up your paper on that day. So, but to some degree, you're going to have to do a little bit of this on your own time now. Okay, I'm done. Perfect. It's 10 o'clock. Thanks, guys.